properties of our complex conjugates. What are we playing with conjugates? How can we use these things to make life easier for ourselves? Well, now we've seen modulus and argument and things like that, we can think of things like this. Well, the modulus of z must be the same as the conjugate, because the only thing we're doing is changing the sign of the imaginary part. So when we go the square root of x squared plus y squared, well, when you square a negative you get the same as when you square a positive. You've got to get the same answer. The argument, however, one will be the negative of the other. And go back to the Argand diagram, we saw it yesterday. When we placed a number and its conjugate, what did we see? It was a reflection in the x-axis. So again, the distance from the origin's the same, but the angle, well, one was above the axis, one was below the axis. So one has a positive, one has a negative. So the argument of z will be the negative of the argument of the conjugate. Now I can stop saying the sum of two squares, because we now know modulus. So another way I can say z times z conjugate is the modulus squared, rather than keep saying the sum of two squared. It's the modulus squared. These are the ones we did see the other day, but just to recap, addition, we can do it whichever way we like. We can add them first, then find the conjugate, and so on. And we saw multiplication, that worked as well. Division, that worked as well. And our reciprocal, I can now express that a different way as well, because I can now say, well, if I want to find the reciprocal of a complex number, it's the conjugate over the modulus squared. And just look at this one example. It's kind of a neat way of showing this result. X plus iy is this particular expression here. Show that x squared plus y squared is equal to 2. Now, there's a very long way of doing it, because you could square both sides and you'd get x squared plus y squared, but then you'd have a 2xy in there. You create simultaneous equations. You can get it this way. But playing with conjugates, we get a really nice, neat way of doing it. X plus iy is that. That's what they've told me. So yes, I am going to square it, but not expand the whole thing out. I'd simply get rid of the square root sign, basically. But let's play with conjugates, because if that's what x plus iy is, the conjugate of x plus iy squared must be the conjugate of 6 plus 2i on 3 minus i. Because conjugate of both sides. But we said with division, well, I could do each individual bit. The conjugate of 6 plus 2i is 6 minus 2i, and the conjugate of 3 minus i is 3 plus i. Well, what about if I multiply these two things together? But each one of those becomes the difference of two squares. So the very first one, I've got x plus iy times x minus iy. That's x squared plus y squared, but it'll be squared. The fraction on the right hand side, I'll have sum of two squares. 36 plus 4, on the bottom of the fraction we'll have 9 plus 1 is equal to 4. Well, that's x squared plus y squared squared. So x squared plus y squared is equal to 2. And I know it's got to be a positive number. I'm not saying plus or minus 2 in this case, because what are x and y? They're real numbers, so when I square them I've got to get a positive number. There's no way x squared plus y squared could be negative 2. Got to be positive 2. Bingo. There it is, done just by playing with conjugates. So in the handouts there, I have copied out the very old textbook, the Patel textbook. It was exercise 4H. Questions 1 to 6 from that.